A black hole weighing 50 million suns was already fully grown before the galaxy hosting it had any stars in it at all. Every textbook says that picture is impossible because the rules we have used for a whole century put galaxies first and black holes second inside them. But the image came straight off the James Webb Space Telescope in raw data, not from a guess, and 3 separate scientific teams have now measured the same kind of thing in 3 separate places. So which one is wrong, the order, the math, or the story we told ourselves about how the first things were built at the start of time? Here is why that question is sharper than it sounds, because the galaxy holding that giant is one of the smallest galaxies anyone has measured at that distance from us. This black hole outweighs the stars around it by something close to 2 to 1, the opposite of what every nearby galaxy shows us in the quiet near universe. Before we walk through what the teams actually measured on the data, hit subscribe and turn on notifications, because the James Webb Space Telescope keeps pointing at new red dots every few months, and we follow each new piece closely here. The people who stay on this channel are the ones reading the deeper lines of these papers, not just the loudest headlines that pass by on the surface at full speed. This investigation is still open, and the next chapter of it is going to land soon, so it pays to be here early in the cycle. What we are about to walk through started with a quiet background assumption that almost everyone in astronomy shared for a long time. Galaxies form first. Gravity pulls huge clouds of hydrogen gas together across hundreds of thousands of light years of mostly empty space. Those clouds cool, they shrink, and the first stars light up inside them, one after another, like candles being lit in a very cold room. A long time passes, and generation after generation of stars live, burn, and finally die across millions and millions of years. Somewhere in that heavy middle, the biggest stars run out of fuel, collapse, and leave behind a small black hole seed weighing only a few tens of suns. That seed then grows slowly over billions of years, swallowing nearby gas, eating unlucky stars, and merging with other black holes along the way. Slowly, that tiny seed becomes the giant we see sitting at the heart of every mature galaxy near us today in the quiet, near universe. That story was the official version for decades, written into every major textbook on cosmology and used in every serious computer model of how the universe evolves. It felt right because it matched what we saw in nearby galaxies, including our own Milky Way, where the central black hole is huge, but the galaxy holding it is far, far heavier. It also matched what older telescopes like Hubble showed when they looked far back in time and saw distant black holes that looked small next to their galaxies, just like the old model predicted. So the rule felt settled in everyone's mind for a long time. Stars first, then small black holes, then bigger black holes, all the way back to the very first moments of cosmic time. But the rule carried a quiet crack hiding inside it, and serious scientists had known about that crack for many years before any of this new evidence actually arrived. If a black hole only ever begins with the death of a single star weighing maybe 100 suns, and the biggest black hole we see today weighs billions of suns, then that tiny seed had to start growing almost the moment the universe began. The math on that was always uncomfortable, and the discomfort grew louder every time someone built a more detailed model of the early universe and ran it forward on a real supercomputer. The numbers kept coming out very tight, almost too tight to be realistic, like pushing a giant through a tiny door in far less time than the giant actually needs. Nobody had a clean answer to that problem, but plenty of people had a quiet feeling that something important was missing from the picture all along. That missing piece is what we are about to walk through, and the tool that finally gave us a way to look at it directly is the James Webb Space Telescope, launched in late 2021 and starting full science work in 2022 after a long deployment in space. Webb sees infrared light, the kind of light that can pass through thick dust clouds and travel across billions of years of cosmic stretching without getting lost on the way to us. Its main mirror is 6.5 meters wide, almost 3 times wider than the Hubble mirror, so it gathers far more light and can see much fainter objects than any telescope that came before it. For a question about the very first black holes and the very first galaxies, that combination of sensitivity, sharpness, and wavelength was exactly what working scientists had been waiting years to get their hands on. Pause with me right here, because the first hard piece of this puzzle is coming up next, and I want you to feel how strange it really is when it lands. Before I tell you about the first object and what the team that found it actually measured, Drop a quick guess in the comments about how heavy you think the first black hole in this story is going to turn out to be. We will come back to your guesses near the end, and you will see whether your gut instinct matches what the measured numbers are now showing from peer-reviewed papers. The first hard piece came from an object the team nicknamed UHZ-1, short for Ultra Hot Zone 1 in their working notes. It sits behind a massive galaxy cluster called Abell 2744, located roughly 3.5 billion light-years from Earth, and that cluster acts like a magnifying glass in space because its enormous mass bends the light from objects much further behind it. That bending effect, called gravitational lensing in the science, made a small distant object look larger and brighter than it would have without the cluster sitting in the way. A team led by Akos Bogdan of the Center for Astrophysics at Harvard and Smithsonian pointed the Chandra X-ray telescope at UHZ-1 in November 2023. Chandra sees high-energy X-rays, the kind that black holes spit out when they swallow hot gas, and the signal came back strong and clean. So strong that the team announced they had found the most distant black hole ever clearly seen in X-ray light, with light from the object traveling for about 13.2 billion years to reach us. That alone was a clean record for the field, but the real shock came when Webb turned its infrared eye on the same spot and tried to weigh the black hole directly, by watching how hard it pulls on the gas swirling around it. The number that came back was roughly 50 million times the mass of our Sun, packed into one single object in a very small space. To feel how big that is, take 50 million suns and squeeze them down into a region smaller than our entire solar system, and imagine the gravity they would all put out together at the center. Now compare that to what was sitting around it, because the host galaxy is what astronomers call a little red dot, a small, compact, deeply red galaxy only seen in the very early universe when galaxies were still babies. Its total mass in stars was far smaller than the black hole sitting in its middle, smaller by a wide margin that nobody could slide past with a casual comment. In nearby galaxies today, the central black hole usually makes up less than 1% of the total mass of the galaxy containing it, a very small fraction in comparison. In UHZ-1, the black hole made up more than half the total mass of the whole system, and careful estimates push that fraction close to 2/3 of everything in that tiny patch of the early universe. That is not a small detail to wave away, because the entire picture of how the old rule was supposed to work was broken in a single, carefully measured data point. Stop with me here, because the next piece is going to look almost exactly like the one I just described, and that is what makes it so unsettling when you see the same story twice from a different team. Before I tell you what a different team found using a different instrument on a different little red dot, drop another quick guess in the comments about whether they also measured a heavy black hole sitting in a small galaxy like the first one. Knowing what you expect before the answer lands is what makes the answer feel real to you, not just something I told you to be excited about. The second piece came from a different team using Webb on a different little red dot nicknamed QSO-1, also written as Abell 2744 QSO-1 because it sits behind the same giant cluster that helped magnify the first object. The lead author on that published paper was Ignas JWST, working at the Kavli Institute for Cosmology at the University of Cambridge in the United Kingdom. His team aimed Webb's near-infrared spectrograph at QSO-1 and split its light into a rainbow to read the chemical fingerprints hiding inside that light as it entered the telescope. That spectrum told them how fast the gas around the black hole was swirling, and from the speed of that swirl, they could calculate down to how heavy the object pulling on the gas really was. The number landed in the same shock range, again roughly 50 million times the mass of our Sun in a single object packed into one place. And again, that black hole made up roughly 2/3 of the entire mass of its tiny host galaxy. The same kind of wild ratio seen with UHZ-1 by a completely different team using a different instrument. JWST put it in unusually plain words for an astronomy paper, saying the team appeared to have found a black hole without a substantial host galaxy that came before stellar processes began in that region of space. Let me translate that single line for you, because every word in it matters here in this unfolding story. By came before stellar processes, he means the black hole got heavy before stars had time to form a real galaxy around it. By without a substantial host galaxy, he means there is no normal galaxy of stars sitting around the black hole yet, just a thin halo of gas and a faint, soft red glow. That is the opposite of what the old rule expected, which was a fully grown galaxy already in place with a small black hole quietly nested inside it at the center. What Webb is showing us now is closer to a giant black hole wearing a thin coat of starlight, almost like a centerpiece wearing a costume it has barely started sewing. Pause here because there is one more big piece of this pattern coming up, and it lands at an even more extreme moment in cosmic time than the first two objects did. Before I tell you what the most distant confirmed black hole yet measured actually looks like, drop a guess in the comments about whether you think it will match the same pattern as the previous two, or whether it will break the pattern in some new way. Write down your guess before you hear the answer, because that guess will tell you something honest about how you actually think the early universe worked back when it was brand new. The third piece of this puzzle came from the most distant confirmed black hole we know of so far. Sitting inside a tiny galaxy scientists have named Capers LRDZ9 in the official catalog files. That discovery was announced in 2025 by a research team at the University of Texas at Austin, working through the Cosmic Frontier Center there. The light from Capers LRDZ9 left it when the universe was only about 500 million years old, just a small early slice of the universe's current age of about 13.8 billion years. And in that single faint, deeply red dot of light, the data once again pointed to a black hole that was heavy compared to the galaxy around it, holding it in place. The pattern was no longer a coincidence at all, because the further back Webb looked, the more often we saw these oddly heavy black holes sitting inside oddly small galaxies that did not fit the old rule. 3 separate discoveries, 3 independent teams of working scientists, 3 separate instruments, 3 separate parts of the sky, all of them pointing to the same uncomfortable picture about how the first things came to be. Black holes were already giant before the galaxies around them were giant, which is not how the textbook said it worked going all the way back. That is not how any of the older telescopes showed it working across 60 years of careful sky watching from the ground and from orbit. Webb was painting a clean, repeatable pattern with each new paper, and the pattern kept getting louder every season for the whole field to see. Hit pause with me for a moment, because the next stretch is the part that tries to actually explain what we are seeing across the sky, and the field is genuinely split right now on which explanation to trust most. Before I walk you through the 3 leading candidate explanations for these overmassive early black holes, drop a quick word in the comments naming which of the candidate explanations you find most believable right now. That guess is a real prediction, not a casual online poll, because real working scientists are quietly disagreeing about this exact question in their conference hallways right now and on long email threads. The first explanation is called the direct collapse model, and it is the simpler one to describe in plain everyday words for any listener. In the direct collapse picture, the black hole does not begin with the death of an ordinary star the way the old textbook said it must. Instead, a huge cloud of primordial gas, the kind of gas that existed before the very first stars ever lit up anywhere in the universe, collapses straight into a heavy black hole seed without ever forming stars in between. If that gas cloud was massive enough, on the order of hundreds of thousands of solar masses of hydrogen packed together in one region, it could skip the middle step from the old story and become a heavy black hole in a single quiet jump. A heavy seed has a much easier time reaching 50 million solar masses in just a few 100 million years, because it begins closer to the finished target weight and has less distance to climb over cosmic time. That is the part of direct collapse that scientists find most attractive as a model, because it solves the awkward timing problem in one neat move without needing any new physics at all. The second explanation is called the super efficient growth model, and it works in a different way than the first candidate does. In this picture, the black hole still starts from the death of a normal star, just like the old rule said it must, but it grows much faster than we thought any black hole could ever grow on regular food from nearby clouds. The fastest a black hole can swallow gas is set by a hard limit in physics called the Eddington limit, named after the British astrophysicist Arthur Eddington, who worked it out a century ago. If a baby black hole eats gas at close to that maximum allowed rate its entire life, with no slowdowns, no pauses, and no competition from anything else around it, then in theory it can still reach 50 million solar masses in the time available. The problem is that the conditions need to be perfect the whole way through, with the black hole always finding fresh gas to swallow and never being pushed back by its own bright glow. That is a very tall order for a baby object sitting inside a messy, chaotic, brand new universe full of pressure from all sides at the same time. The third explanation is the most interesting and also the most controversial, and it has been floating around in theoretical physics for decades without a confirmed example in real nature so far. This third candidate is called primordial black holes, and they would not be born from stars or from collapsing gas in the usual astronomical sense at all. They would have formed in the very first fractions of a second after the Big Bang, when the universe was wildly dense, wildly hot, and full of sharp differences in pressure from one tiny region to the next nearby region. In some theoretical models, those sharp differences were extreme enough to crumple parts of space into black hole seeds before any stars, any galaxies, any of the structures we recognize today even existed. If primordial black holes are real, and if some of them were heavy enough to start with, then they could be the missing first seeds for the giant black holes Webb keeps finding everywhere with each new survey. You do not need special gas to collapse in a particular way at all in this picture. You do not need a baby black hole to eat at the maximum possible rate its entire life without ever being slowed down. You just need to allow for black holes that started earlier than anything else in the universe by a long margin from the very first tick of the cosmic clock. Stop with me one more time, because the next stretch is the part where we walk the whole case back to the opening claim and try to settle it properly out in the open. Before I tell you what the verdict on the opening claim looks like as of mid-2026, drop a prediction in the comments about whether you think the opening claim was basically right, or whether you think we will end up overturning some part of it when all the dust settles. That is also a real prediction you can compare later with what working scientists are quietly disagreeing about right now in their conference hallways. Let us take a step back and remember what the opening claim of this whole script actually said out loud. It said, a black hole weighing 50 million suns was already fully grown before the galaxy hosting it had any stars in it at all. The careful question underneath it asked which part of our old picture of the cosmos was wrong, and what working scientists should put in its place for the next generation to learn from. Now we can answer that question honestly based on what the evidence actually shows, not based on what textbooks were sure of 50 years ago when nobody could see this far back into the universe without much better tools. The black hole is real, and it really is about 50 million solar masses in every confirmed case so far across the 3 separate objects I have walked you through here on this journey. The host galaxy really is unusually small and unusually young, much younger and lighter than the galaxies we normally see hosting such heavy black holes in the nearby universe today close to home. The picture we used to call impossible is in fact exactly what the data is showing us, just measured in 3 different ways by 3 different kinds of instrument, by 3 different teams of working scientists in their own labs. So the first half of the opening claim holds up cleanly against the measurements that came in across more than one peer-reviewed paper from separate research groups. The hidden question underneath the opening was harder, and the answer to that one is sharper than it first sounds on the surface. Which part of the old story was actually wrong? The answer, as of mid-2026, is that the old order was wrong, and not just by a small amount we can fold away in a footnote. The black hole is allowed to come first in the order of things out in the cosmos. The galaxy is allowed to grow up around it much later in cosmic history under the right conditions. The old rule that said the galaxy had to come first and the black hole had to grow slowly inside it is now the suspect, not the assumption we can take for granted anymore. The old textbooks were not lying when they were written by very careful people with the tools they had at the time. They were the best version of the truth at the time, using the instruments that were actually available back then. The universe simply offered more evidence as the tools got better over the years, and the people with those new tools paid close attention to what the new evidence was quietly saying all along. The verdict in plain words is this: black holes can and apparently often do form before their host galaxies exist in the way we usually picture them. The leading explanation right now is that some early black hole seeds were much heavier than the old story allowed, most likely through the direct collapse of massive primordial gas clouds in the very early universe. A second possibility, very hard to rule out from current data alone, is that some black holes were born even earlier than any gas cloud, as primordial seeds from the very first moments of the universe itself. The old textbook story, while not entirely wrong in every chapter, is now confirmed to be missing at least one important chapter that nobody noticed before Webb started looking this far back with such fine detail. Now let us pull the camera back even further and talk about why any of this should matter to someone sitting on Earth far from any telescope watching the sky on a quiet night. It matters because it changes how you think about the universe you live inside from the ground up in a fundamental way. The night sky feels calm and finished, like everything out there has been in place forever in roughly the same way since the beginning. But under that calm, the universe is now telling us that the order in which its biggest pieces appeared is not the order we were taught in school at all in the older generations. That is humbling, and it is also exciting, because it means the map of the cosmos is still being drawn by people alive today with new tools and new eyes. Some of the biggest landmarks on that map are being moved while we watch, in papers that are being written right now in research offices on several continents at the same time of year. It also matters because the method behind the answer is worth seeing clearly on its own terms as a piece of working science. The textbooks were not lying when they were written by very serious scientists with great care and patience. They were simply the best version of the truth at the time, built from the best tools available back then in the previous generation of observatories in orbit and on the ground. The universe offered more evidence as new tools got built and launched into space over the past few years and decades. The people with those new tools paid close attention to what the new evidence was actually saying, even when it disagreed with what they had written in their own earlier papers from earlier careers. That is what working science actually does in the open, and watching it happen in real time is one of the most honest things human beings ever do as a community together. There is also a personal layer to this story that I do not want to skip past without naming it out loud here. Every single one of us is made of atoms that came out of stars that lived and died inside galaxies like the ones we have been talking about here on this deep journey. Carbon in your fingers when you touch a key on a keyboard or pick up a cup of something warm in the morning. Calcium in your bones that hold you up every day of your life under gravity. Oxygen in every breath you take in and out of your lungs every minute of every hour of your life on this planet. So when we look 13 billion years back and see black holes sitting where galaxies should be, we are looking at the conditions that eventually led to us being here at all on this small blue planet. The story of how those first giant black holes came to be is part of the story of where we all came from in a very real physical sense, tied to actual atoms in our bodies. That is what makes this puzzle worth following carefully, even when the answer is not yet fully clean across every chapter of the unfolding case. And the story is far from finished, because as of mid-2026, the number of confirmed overmassive black holes in the early universe is still climbing steadily. With every new paper that lands in the journals, the number of competing explanations is small but very active in research circles right now across the world. New Webb observing programs are pointed at more of these red dots across the sky as we speak in this observing cycle. Each one of them is being weighed, measured, chemically tested, and modeled against the three leading explanations in careful detail by serious teams in multiple institutions. Each new result will either tighten the case for direct collapse of primordial gas or quietly open the door wider for primordial black holes from the very first moments of the universe. And the verdict may tighten further, or partly reverse in some chapters, as more careful data lands in the next year or two from new observing cycles now underway at multiple observatories around the world. Here is what I want you to do next, because the case is not over, and your guess still matters in the way the public conversation about this is going forward in the next few years. Drop a comment telling me whether the current working name for these objects, little red dots, still feels right to you after everything you just heard across this whole script, or whether you think they deserve a brand new name that flags them clearly as black hole first objects for the next generation of students and researchers to use in their papers. That is a small word choice on the surface, but the words we use will shape the next 10 years of how this is taught in classrooms and searched for in deep surveys across the field. If this kind of careful, honest look at unfinished science is what you stay on this channel for, then subscribe and turn on notifications right now, because we go deeper on stories like this every single week when a new paper lands in the journals. Drop a comment with your answer to the prediction question I asked earlier about what the verdict on the opening claim should turn out to be in the long run of the investigation. And tell me which of the three candidate explanations you trust the most right now, and why in your own plain words in a single sentence, so the community can read it and think about it. If you know someone who would lose sleep over this kind of cosmic puzzle, send them this video right now while the next chapter is still fresh, because they should be here when the next paper lands at the observatory. Thanks for staying all the way through this one with me, and for letting me walk you through the slow build instead of just the loudest headlines from the press release on the surface. We will pick up the next piece of this story the moment it lands from the next round of papers coming out of the teams at Harvard, Cambridge, and the University of Texas at Austin across multiple continents.